Hello everyone, welcome to Power Electronics. In this session, I will be discussing the BJT switching limits. BJT has 5 switching limits as listed here. The first one is the second breakdown, also called as secondary breakdown. Then forward biased safe operating area, denoted by FBSOA. Third is the reverse biased safe operating area, denoted by RBSOA. Fourth is the power derating, and the last one is the breakdown voltages. Let us now discuss each one of them in detail. The secondary breakdown, which is a destructive phenomenon, results from the current flow to a small portion of the base, producing localized hotspots. If the energy in these hotspots is sufficient, the excessive localized heating may damage the transistor. Thus, secondary breakdown is caused by a localized thermal runaway resulting from high current concentrations. The current concentration may be caused by defects in the transistor structure. The secondary breakdown occurs at certain combinations of voltage, current, and time. Since time is involved, the secondary breakdown is basically an energy dependent phenomenon. The secondary breakdown can occur under forward bias and reverse bias conditions. The application of reverse base drive will cause base current in the reverse direction. However, the potential gradients may reverse bias only the periphery of the base, where the center of the base may still be forward biased. The current may be flowing in a small area toward the center of the base, resulting in current concentration forming a hotspot. Coming to the second switching limit, which is the forward biased safe operating area. During turn on and on state conditions, the average junction temperature and secondary breakdown limit the power handling capability of a transistor. The manufacturers usually provide the FBSOA curves under specified test conditions. FBSOA indicates the IC versus VCE limits of the transistor, and for reliable operation, the transistor must not be subjected to greater power dissipation than that shown by FBSOA curve. Several different physical mechanisms are active in determining the boundaries of the FBSOA as shown in the diagram here. The current ICM is the maximum collector current even as a pulse that should be applied to the transistor. Exceeding this current may cause bonding wires or metallizations on the wafer to vaporize or otherwise fail. The thermal limit is a power dissipation limit set by the thermal resistance of the transistor and the maximum allowable junction temperature. The secondary breakdown boundary represents the maximum permissible combinations of voltage and current without getting into the region of IC versus VCE plane where the secondary breakdown may occur. The final portion of the boundary of the FBSOA is breakdown voltage limit BVCEO. If the transistor is operated as a switch, then the boundaries of the FBSOA expand. The expansion of the safe operating area occurs for switch mode operation because the silicon wafer and its packaging have a thermal capacitance and hence an ability to absorb a finite amount of energy without the junction temperature rising to excessive levels. If the transistor turns on in a few microseconds or less, the amount of energy that is absorbed is too small to cause any appreciable rise in the junction temperature, and as a result, the FBSOA is essentially square, being limited only by ICM and BVCEO. Coming to the third switching limit, the reverse bias safe operating area. During turn off, a high current and high voltage must be sustained by the transistor. In most cases, with the base to emitter junction reverse biased. The collector to emitter voltage must be held to a safe level at or below a specified value of collector current. The manufacturers provide IC versus VCE limits during the reverse biased turn off as reverse bias safe operating area. The area encompassed by RBSOA, which is a pulsed safe operating area, is somewhat larger than the forward bias safe operating area because of the extension of the area of higher voltages than VCEO up to VCBO at lower collector currents. The operation of the transistor up to the higher voltage is possible because the combination of low collector current and reverse base current has made the beta small so that the breakdown voltage rises towards VCBO. Coming to the fourth switching limit, we have the power derating. The derating factor of a transistor is the amount by which the power dissipation rating of a transistor falls when the transistor junction temperature increases. Here we have shown the thermal equivalent circuit of a transistor. Let us now indicate some of the notations here. Tj represents the junction temperature, Tc represents the case temperature, Ts represents the sink or which is the heat sink temperature, and lastly Ta represents the ambient temperature. Finally, coming to Pt, it is the total power loss. Now let us look into each one of these notations and discuss what they are. Starting with the case temperature. Case temperature is that temperature measured at a specified point on the case of a semiconductor device. In some cases, a transistor derating curve is provided for ambient temperature, while in other cases, the curve covers case temperature. In either case, the derating curve indicates what factor is being measured. Temperature to power derating curves are also provided for a particular transistor case style without regard to any semiconductor device. Coming to the heat sink now, it is a metallic device that dissipates or radiates heat into the surrounding which is generated from an integrated circuit or other device. There are a number of materials used for heat sinks such as aluminium, brass and bronze. There is also a large section of heat sink styles such as folded fins, bonded or fabricated fins or stampings. The point of the heat sink is to increase the surface area affected by the surrounding air. Most air-cooled heat sinks are convection limited, and the overall thermal performance of an air-cooled heat sink can often be improved significantly if more surface area can be exposed to the airstream. Such high-performance heat sinks utilize thermally conductive aluminum-filled epoxy to bond planar fins onto a grooved extrusion base plate. Metal heat sinks are available for plastic packages as well as metal cans. Now coming lastly to the ambient temperature, it is the air temperature measured below a semiconductor device in an environment of substantially uniform temperature, cooled only by the natural air convection and not materially affected by the reflective and radiant surfaces. Note that free air is also called still air and also implies that the device is not installed with an electronic chassis that would restrict airflow. Junction temperature, as we know, is the temperature of the junction of the transistor. Now, if the total power loss is represented by Pt, then the case temperature Tc is given as Tc equals Tj, which is the junction temperature, minus the power loss multiplied by Rjc. We will write that here. So Tc equals Tj minus Pt into Rjc. Coming to the sink, which is the heat sink temperature, Ts equals Tc minus PT into RCS. We'll write down that also. TS equals TC minus PT into RCS. Lastly, the ambient temperature, which is given by TA, is equal to TS minus PT multiplied by RSA, which is written here. TA equals to TS minus PT into RSA. So, if you want to find the temperature of the device, then it is simply the difference between junction temperature and ambient temperature. By applying these equations into Tj minus Ta, we find that it is equal to Pt multiplied by the addition of all of the thermal resistances of the corresponding junctions, which is RJC is called as the thermal resistance between junction to case. RCS is the thermal resistance between case to sink. Lastly, RSA is the thermal resistance between sink to ambient. Note that all of these are measured in degree centigrade per watt. Coming back to the circuit diagram here, the maximum power dissipation PT is normally specified at Tc equals 25 degrees centigrade. At higher temperatures, the power dissipation rating is less. For example, if the ambient temperature is raised to 150 degrees centigrade, the transistor can dissipate zero power. On the other hand, if the junction temperature is 0 degrees centigrade, the device can dissipate maximum power, and this is not practical. Therefore, the ambient temperature and thermal resistances must be considered when interpreting the ratings of the devices. For most silicon transistors, the maximum allowable junction temperature is between 150 degrees centigrade and 200 degrees centigrade. Temperatures higher than this will destroy the transistor. This is why a manufacturer must specify a maximum power rating for the transistor. The transistor's power dissipation rating must be kept to less than its rated value so that the junction temperature will not reach destructive levels. Manufacturers usually supply derating factors for determining the power dissipation rating to any temperature above Tc of 25 degrees centigrade. The derating factor is specified in watts per degree centigrade. For example, if a transistor has a derating factor of 2 milliwatt per degree centigrade, then for each 1 degree centigrade rise in junction temperature, the power rating of the transistor is reduced by 2 milliwatts. Coming to the last of the switching limits, we have the breakdown voltages. A breakdown voltage is defined as the absolute maximum voltage between any two terminals with the third terminal open, shorted, or biased in either forward or reverse direction. At breakdown, the voltage remains relatively constant, whereas the current rises rapidly. The following breakdown voltages are quoted by the manufacturers. The first one we have is VEBO. It is the maximum voltage between the emitter terminal and base terminal with the collector terminal open circuited. The second one is VCEV or VCEX. It is the maximum voltage between the collector terminal and emitter terminal at a specified negative voltage applied between base and emitter. Lastly, we have VCEO sustain. It is the maximum sustaining voltage between the collector terminal and emitter terminal with the base open circuited. This rating is specified at the maximum collector current and voltage appearing simultaneously across the device with a specified value of load inductance. So, that was about the discussion on the switching limits of the BJT. Thank you.